Assalamualaikum and good afternoon everyone. So this video lecture for chapter 3, Model Reference Adaptive Control, MRAC. So for this chapter 3, at the end of this chapter, you will be able to understand or describe the principles of MRAC. You will be able to design the MRAC using the gradient method or MIT rules, and you will be able to design the MRAC using the Lyapunov method. Okay, this slide shows the structure of the MRAC. So this is the structure of the MRAC. There are 4 main components of the MRAC, which are number 1 is the plant. Okay, number 1 is plant to be controlled. Number 2 is the reference models that to produce a desired output response. Okay, we label the response as YM. Okay, we label the output response for the plant as Y. Okay, and then number 3 is controller, where the controller is time varying, and the parameter of the controller can be adjusted by using the adaptive mechanism. Okay, the parameter can be adjusted by using the adaptive mechanism. And number 4 is adaptive mechanism, okay, that use error, okay, to produce the controller coefficients. So adaptive mechanism use error to produce controller parameter, okay, coefficient, controller parameter, okay, where error is the difference between the output response of the plant Y minus the output response of the reference model YM. So here is the error. So the adaptive mechanism will use the error between the reference models and the plant to produce a controller parameter. So this basically the structure of the MRAC and what MRAC is all about. There are 2 types of MRAC, which are number 1 is gradient method or MIT rules, and number 2 is Lyapunov method. Okay, so there are 2 types of MRAC, which are the gradient method or MIT or Lyapunov method. Okay, from previous slide, we already know that there are 2 types of MRAC design method, which are gradient methods and Lyapunov method. So first we start with the gradient method or MIT rules. Okay, so MIT rule was first developed by Massachusetts Institute of Technology, MIT, USA. So it is relatively simple and easy to use. he said. Okay, simple and easy to use. And in this method, we will like the output of the closed loop system Y to follow the output of the reference models YM. Okay, if you still can remember from the previous slide, okay, in the structure of MRAC, okay, there are summing junction. Okay, compare between the reference models. Okay, so here is YM and plant. Okay, the output of the plant we label as Y, and the error between the plant output response and the reference model output response we call as error, and become the input for the adaptive mechanisms. Okay, so based on the error value, the adaptive mechanisms will produce the controller parameter or the controller coefficients. Okay, because we want to make sure that we will be able to minimize the error. Okay, and the output of the plant Y follow the output of the reference model YM. So we want to minimize the error. Okay, error is equal to Y minus YM. You want to minimize the error, okay, by designing a controller that has a 1 or 2 adjustable parameter based on the error itself. Okay, so I think that's for the gradient method or MIT rules. Controller design method for MRAC. Consider a closed-loop system with a controller that has only one adjustable parameter theta. Let RT equal to reference input signals, UT equal to control signals, YT equal to plant output, YMT equal to reference model output, and ET equal to difference between plant and reference model output, YT minus YMT. The control objective is to adjust the control parameter theta so that ET is minimized. So to do this, a cost function j theta is chosen and minimized. Possibility 1. Adjust theta such that cost function j theta equal to 0.5 error squared is minimized. So to do this, we need d theta over dt equal to minus mu dj over dt. Okay, so this is equation 1. Theta is changed in the direction of negative gradient of j, where the negative sign implies that theta is changed. Okay, so negative sign means that theta is changed such that j becomes small. Okay, so from 1, here from equation 1, dt over d theta over dt equal to negative mu d negative phi dj over dt equal to negative phi dj over de times de over d theta. So this will become, we will get again d phi error d error over d theta. So d error over d theta is called the sensitivity derivative, which indicate how the error is influenced by the adjustable parameter theta. Okay, d error over d theta. Okay, possibility 2. In possibility 1, possibility 1, okay, we choose j theta equal to 1 over error squared. But in possibility 2, so we will adjust theta such that the cos function j theta is equal to modulus, and this function we have to minimize. So we then have d theta over dt equal to negative phi dj over dt, where dj over dt is equal to dj over de times de over dt. So dj over d theta is equal to dj over de times de over d theta. So dj over de is come from this equation. Okay, so dj over de is equal to sine e. So from this equation, we will get d theta over dt is equal to negative phi de over d theta times sine e, because dj over de is equal to dj over de is equal to sine e, where sine e is equal to positive 1 if e is greater or equal to 0, and negative 1 if e is less than 0. So this is the possibility we have to consider in possibility 2. Okay, now controller design examples. Consider a linear process with transfer function kgs is linear and k is an unknown parameter. Find a feed-forward controller that gives the system a transfer function gms equal to k naught gs, where k naught is a given constant. Let then controller be ut equal to theta rt. Okay, so now we want to design a MRAC for the given plant. Okay, this is the control system structure for this particular examples. I have go through this structure in the slide 1 or 2, still can't remember, but I think I have go through every blocks and function and its functions. So as a revision, we will go through it again. Here is the reference models. This block is the adaptive mechanisms. Okay, here is the controller. Here is the plant you want to control. So ym is the output of the ymt is the output of the reference models, while yt is the output of the plants. So the difference between the plants and the reference model is error. Error is equal to yt minus ymt. Okay, so theta is the output of the adaptive mechanism, theta t. Okay, so ut is the control signals, ut. So this is the output of the controller and become the input for the plants. And reference models we noted as RT. So what's the information that we get from the questions? Given that the plant models KGS, where K is known, K is unknown, unknowns. So output over inputs is equal to KGS. Okay. The reference model given is GMS equal to K naught GS, where K naught is known. Okay, so output YM over input, the reference signals are equal to K naught GS. Okay, the controller UT equal to theta RT. The cost function given is the cost function that we have choose is possibility 1 J theta equal to 1 over 2 exponent squared. Okay, so let's say if we choose possibility 1 to solve these questions, so what's the solutions? You may choose either possibility 1 or possibility 2. It's up to you and the suitables of the solutions. Okay, so d theta equal to 1 over 2 exponent squared. So dj over de is equal to dj over equal to e. Okay. So to design the MRAC controller, we must aim to find the adjustable parameter theta. Okay, so this is the adjustable parameter theta. Okay. So, okay, for next slide. Okay, in order to find the adjustable parameter theta in order to design the MRAC, okay, now we want to determine theta. Okay, so the equation that the theta can be found is in this equation, d theta over dt equal to negative phi dj over dt. Okay, so theta can be found in these equations. And since we choose the cost function j theta equal to 1 over 2 exponent error squared, so dj over de is equal to error. So, okay, so from this equation, negative phi dj over de times de over d theta. Okay, so from here, dj over de is equal to e. So negative phi e de over d theta. To find de over d theta, we need to find the expression of e in terms of theta. So we also know that error e is equal to y minus ym, where y is equal to kgs u and ym equal to k naught gs r. Okay, and u is the controller is equal to theta r. Okay, so substitute all of these equation in E equal to y minus ym. Okay, so y is equal to k gs u minus ym is k naught gs r, and we also know that u is equal to theta r, so substitute the equations. K gs theta r minus k naught gs r. So dE over d theta is equal to k gs r. Okay, so this equation 2. So d theta over dt is equal to negative v dj over d theta, okay, equal to negative v dj over de times de over d theta. Okay, so since we choose the cos functions, j theta over 1 over 2 error squared, okay, so dj over de is equal to error e. So substitute in the equations, we will get negative v e times de over d theta. So phi is the value to be selected later, okay, to be selected later. E is known signals, and sensitivity derivative is something to be found, okay. So as we have derived in previous slides, we have get dE over dt equal to k gs r. Okay, so therefore dE over dt is equal to negative v e k gs r. Okay, so however, we can see from the MRAC structure, okay, that we cannot directly get the signal k gs r. So now we will start from ym equal to k naught gs r, okay, in order to find the value of k gs r. Okay, so ym equal to k naught gs r. So gs r is equal to ym over k naught. Okay, so now we want to find the value of k gs r. So what we have to do is multiply k in both equation. So k gs r equal to ymk over k naught. So substitute in the equations. D theta over dt equal to negative v E KGSR. So KGSR is equal to these equations, negative V E times YM K over K naught. From previous slide, d theta over dt is equal to negative VE Ym K over K naught, where phi, K and K naught is a constant value. Okay, so now we assume phi K over K naught is equal to A, so d theta over dt is equal to negative A exponent error Ym. Okay, so now by using Laplace transforms table, okay, so this Laplace transform table, you have to remember the table will not be given in any examinations. So theta equal to negative A error Ym over S. So this is the value of theta, the one that you want to find, or the adjustables parameter that we want to determine. Okay, now this is the original control structure before we obtain the equation for theta. Okay, theta equal to negative A error Ym over S. Okay, so Ym is here. We get Ym is from here. Here is the error. Okay, so now what we want to do is that we want to change the structure of the controller or the structure of the MRAC after we get the equation for theta. Okay, so in the theta equations, we have negative A E Ym n over S. Okay, now we erase. Okay, we have to draw it again. By using the pen, the red color pen. Okay, so Ym, okay, times E. Okay, so Ym times E. Here we get Ym error. Okay, Ym error. So in the blocks, negative A over S. Okay, so here is theta. Okay, so theta is equal to negative A Y ME over S. Okay, and theta, okay, times R. Okay, theta times R is equal to the U. So U equal to theta times R. Okay, so if we draw it again, okay, in the next slide. Okay, so if we draw it again, okay, pen color, red pen color. So K naught GS, okay, output is Ym. Ym, here is Y, okay, from the plant. KGS, is the plan. Okay. So now theta is equal to negative A y m e over s. Okay. So ym here is e error. So ym times error. Here is ym e. Okay. So ym e in the blocks negative a over s. So the output theta is equal to theta is equal to negative a ym e over s. Okay, so here is the reference signals RT. Okay, so the output UT, U equal to theta RT. So here is U. So U is equal to theta times RT is U. Here is UT. UT is the control signal for the plant. Okay, the output of plant is the Y, the output. So theta is the adjustable parameter that we want to find. Okay, so we through the calculation we'll define the equation for theta. And again, reference input is the reference signal is the input for the reference models. Okay, so here is the MRAC control structure. Okay, we determine the equation of theta, and then we change the structure of the control structure. We change the structure of the MRAC. Okay, based on the equation of theta that we already get. So for example 2, from previous examples, if k equal to 1 and k not equal to 2, gs equal to 1 over s plus 1, gms equal to 2 over s plus 1 equal to ym over rs. So how is the structure, the control structure and the value of the theta and so on. So these will be the short assignments, okay, for all of you. So we will discuss in the next video lecture. Okay guys, so I think we have another subtopics, how to design MRAC for Lyapunov. Okay, so after that we will have another one assignments and one quiz. So after all of this, you are ready to go for final exams. Okay, I will discuss a few final exam questions, set of questions. So I think that's all for this week. Okay guys, thank you very much.